This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. One of the biggest challenges facing mankind today is our quest to transition to renewable energy. Overhauling our entire electricity grid requires drastic changes to be made in the way we produce, transport, use, and store electricity. We have explored in past videos that with the lowering cost of solar and wind, we are beginning to hit a point of imbalance in the grid, where places like California are wasting massive amounts of energy in the summer months when solar is at its peak and not producing enough in winter. To deal with this problem, California is now installing gigantic battery storage facilities in places like Moss Landing to store that excess for later use. But the amount of battery storage that they will require as our percentage of renewables increases is going to cost the state billions, if not trillions. We could drastically decrease this dependence on batteries if we could find a nice, stable energy source that did not harm our planet. Some want to turn to nuclear energy, but what if I told you the solution may be lying directly under our feet? Imagine an ancient, hidden energy source deep within every square meter of our planet's surface. It's clean, flexible, virtually limitless, completely renewable, never turns off, and virtually carbon-free. Geothermal energy is produced by the Earth's inherent heat. The center of the Earth is as hot as the surface of the Sun. Through convection, that heat warms the outer layers of the planet. But where does that heat come from? Much of it comes from gravitational forces when the planet first formed 4 billion years ago. Some heat is generated from friction as denser elements make their way to the Earth's core. The other source of Earth's internal heat occurs in the upper mantle and crust, where the decay of radioactive isotopes like potassium-40 creates energy and in turn, heat. If we could find a way to safely and cost-effectively access that heat, our energy problems would be solved in years. That heat does come to the surface in some easily accessible locations. At temperatures of 700 degrees or more, rocks become partially melted, becoming magma, driving a variety of geothermal phenomena. If magma flowing underground heats gases or water, it can create bubbling hot springs and geysers, undersea hot vents, and natural steam vents. These features can provide water that's more than 200 degrees, more than enough to run a steam turbine. Geothermal hotspots like this are found near the boundaries of tectonic plates like Iceland, in volcanically active areas like Turkey, or in some places where the Earth's crust is thin, like America's Yellowstone National Park. These places provide low-hanging fruit to harvest the Earth's heat for our energy needs. Each year, enough heat flows to the planet's surface to meet our total global energy consumption twice over. And the geothermal reservoir is boundless. Heat within 10 kilometers of Earth's surface contains roughly 50,000 times more energy than all fossil fuel resources worldwide. Yet, geothermal energy makes up less than 1% of global installed electricity capacity. This isn't even a technology issue. Of the global potential for geothermal power using off-the-shelf technology, only 7% has been tapped. So, in the fight to transform our global energy system, why haven't we adopted this energy source in a serious way? Let's first look at our low-hanging fruit that are not being used to their full potential. Naturally occurring hydrothermal reservoirs feature hot water that percolates near the surface through porous or cracked rock layers. This is the easiest form of geothermal energy to harvest and can be tapped in several ways, which we've been doing for centuries. Human societies have used the heat from low-temperature geothermal energy for millennia. Among the most famous examples may be the hot springs of Bath, England, established by Roman engineers in 60 CE. Here, 1 million litres of water percolates to the city centre of Bath every day at a temperature of about 45 degrees, heating recreational baths and heating some buildings. This hot water replenishes itself as rain that falls in nearby hills seeps through porous limestone deep underground where it is heated and rises back to the surface. But convenient locations like this, where the right combination of a water cycle with porous rocks underground and a heat source close enough to the surface to heat it, are rare, and ones that can provide water with enough heat and pressure to run a steam turbine are even rarer. This particular source is not suitable as 45 degrees is far off the lowest temperature we can employ. There are three basic types of geothermal energy generators. All three share the same basic idea. Take hot water or steam from a geothermal reservoir and run it through a steam turbine where it loses energy and condenses before being pumped back underground to keep the cycle going. Dry steam generators take the steam directly from the source to run the turbine. A flash steam power plant takes extremely hot water under pressure above 100 degrees and expands it quickly to lower its boiling point and turn it to steam to run the steam turbine. These both require higher temperature sources that are rare but are relatively common in geothermally active regions like Iceland, Italy, Austria, and around the Pacific Ring of Fire, and in these locations, geothermal energy is common and is expected to grow as much as 28% in the next 4 years, with countries in Southeast Asia expected to see the largest growths, like Indonesia and the Philippines. But we want to exploit geothermal energy outside of these regions. No matter how much power we extract, we can't transport it far before power losses due to resistance in the cables saps it away. The third type of generator provides the highest potential for expanding geothermal energy as it can utilize the lowest temperature sources. This system is called a binary cycle system. In a binary cycle power plant, warm water from a geothermal source passes through a heat exchanger where it exchanges heat with a closed loop containing a fluid with a low boiling point, like pentane, which has a boiling point of 36 degrees. The lower boiling point allows it to transition to a gas at a much lower temperature, allowing it to run a turbine at a lower temperature. This system has allowed countries like Germany, which lacks any shallow depth geothermal resources, to grow their geothermal energy market in recent years, with temperatures as low as 100 degrees Celsius being utilized. That figure is important because the higher the temperature, the deeper we have to drill. Different areas have different geothermal gradients, which is a measure of how quickly temperatures rise as we drill down. This map shows a rough estimate of the geothermal gradient across the US, with the highest gradients being found in Oregon and Idaho, reaching as high as 70 degrees per kilometer. This is important as to access this heat in areas where it doesn't naturally come to the surface in an accessible way, we need to drill down, and the further we need to drill, the more expensive it becomes. Typically, we have only used geothermal resources where the natural permeability of the rocks allows a convective heat cycle. But a new technology by the name of Enhanced Geothermal Systems, or EGS, may open the door to geothermal energy in more regions. It works like this. The first step is to drill an injection well into a formation of hot rocks. Then, engineers inject fluid at pressure to form cracks or enlarge existing ones. This increases the area over which heat exchange with the rocks can occur. To increase this area even further, a non-toxic and degradable material is pumped down to fill these cracks and allow the pressure to form new cracks as we drill further down. Once we have opened an adequate number of passages for the water to fill, we can drill additional holes that can act as an outlet for our hot water as we pump more underground. A report by MIT in 2006 found that EGS could provide electricity at a cost as low as 3.9 cents per kilowatt hour, roughly equivalent to a coal-fired power plant. The United States government estimates that new geothermal power plants could produce 60 gigawatts of electric power on American soil by 2050, mostly through EGS systems. Now, I know what you are thinking. This sounds a lot like the controversial practice of fracking, but it doesn't use toxic fracking fluid, which can seep into our water cycle. It uses water and some safe additives. But it's not all plain sailing. To make this work, we need to create great volumes of fractures and cracks, and this can have some disastrous consequences. In 2017, drilling at a proposed site for EGS in Pohang, South Korea, is thought to have triggered an earthquake of 5.4 magnitude that injured 135 people. A previous incident occurred at an EGS plant in Basel, Switzerland in 2006, when drilling may have caused a quake of magnitude 3.4 and several buildings were damaged. Both projects were cancelled as a result. Red tape is a huge obstacle for geothermal energy. In the United States, for example, There's less environmental paperwork and fewer approvals required for drilling for oil than drilling a geothermal well. Tax credits for wind and solar power projects are 30%, while the tax credit for geothermal is only 10%. On top of all this, drilling is very expensive, and, as we have seen, doesn't guarantee a successful geothermal plant. You could waste months of your time digging a 2-kilometer hole in the ground, and the productivity of the well could be too small to make the project worthwhile. This makes it difficult to find investors willing to bet their money on it. It simply makes more sense to invest in solar and wind. Despite the challenges, there's real hope for expanding geothermal energy. The industry can build off of recent improvements in drilling technology. Engineers are developing new kinds of drills for geothermal wells and better techniques for cementing wells drilled into hot rocks. The earthquake risk is real, but engineers have protocols for monitoring with seismometers to ensure that the seismic risk can be assessed early on. In the case of the Basel accident, the EGS facility was located over a seismic fault due to the proximity of hot rocks to the surface. Once the shaking started, fluid injection was halted immediately. So far, geothermal projects haven't attracted strong political support in the West, but they also haven't managed to draw major opposition, suggesting that easing permitting rules for the technology may not be so challenging. As commercial interest in this clean energy source rises, political support for it should follow, especially if some smart politician realizes that it can be a rallying call for getting out of work oil drilling techs back to work. Sometimes the struggle to convert the global energy system to renewables can seem out of reach and feel hopeless, but in the case of geothermal energy, there's an exciting source of electricity and heat that could power our future, and it's right below our feet. As I said at the start of the video, much of the energy present within the Earth is formed as a result of gravitational forces. You can learn everything gravity is capable of by taking this course on Brilliant. This course will take you from the very basics of what gravity is and build your knowledge up to the point of being able to apply Kepler's laws of planetary motion and understand orbital mechanics, like using the slingshot effect where spaceships use a planet's gravity to increase their speed. It's a fascinating course that I can't recommend enough. Or you could complete one of Brilliant's daily challenges. Each day, Brilliant presents you with interesting scientific and mathematical problems to test your brain. Each daily challenge provides you with the context and framework that you will need to tackle it, so that you can learn the concepts by applying them. If you like the problem and want to learn more, there's a course quiz that explores the same concept in greater detail. If you are confused and need more guidance, there's a community of thousands of learners discussing the problems and writing solutions. Daily challenges are thought-provoking challenges that will lead you from curiosity to mastery, one day at a time. If I've inspired you and you want to educate yourself, then go to brilliant.org/real engineering and sign up for free. And the first 500 people that go to that link will get 20% off the annual premium subscription, so you can get full access to all their courses as well as the entire Daily Challenges archive. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.